We will now consider a couple of consequences of these two theorems. They are not as important as Lax-Milgram's lemma and the theorem connected to the minimum formulation above, but they are also interesting, and such results are often called propositions. So let's just consider proposition 1 first. If the condition 2 and 4 are satisfied, then this energy functional f of phi turns out to be continuous. That is, if we have a sequence of functions in the space V, let's call them phi n converging to phi. That means that the difference between these functions and phi turns to 0. In the norm of them, at least, turns to 0 when n goes to infinity. So that's the definition of convergence in these spaces. Then we should have that also the energy functional f of phi n converges to f of phi. And as usual, we just recall that f of phi is equal to half of a of phi minus L of phi. So when these two conditions are satisfied, just recall these conditions. We remember that it was connected to continuity, and the next was the V ellipticity. So then we obtain this result. So that implies the convergence or the continuity of this functional. Another interesting result is the following. If the property 3 and 4 are satisfied, then and you know that 3 was concerning the V ellipticity of this functional, and 4 was connected to the continuity of the linear form L. If this is satisfied, then f of phi turns to infinity when the absolute value or the norm of phi turns to infinity. I understand that this may seem a little bit complicated and strange, so let's just compare with a more simple example in R1, or in the case of real functions, usually real functions. Let's just define a function f1 of x in this way. We'll let it be 2x when x is larger than 0, and minus 2x plus 1 when x is less or equal to 0. So let me just show you the graph of this function. It looks like this. So in this case, we obviously see that there exists no minimum point of this function. The minimum could have been 0, but the function is not continuous, so it jumps from something very near to 0 and up to this value when we approach 0. So for the value x equal to 0, the function is a different from what it was close to 0. So we observe that the lack of continuity, which was the conclusion of the first proposition, the lack of continuity of f is not a very good property. In fact, it's possible to show that if these two propositions are satisfied, or let's say it in a different in different words, if the functional f is continuous and f has this property, then it's possible to show that this functional has a minimum. So let's just see that, give you examples where these properties are not satisfied. So here we got an example where the lack of continuity implied that the function does not have any minimum point. Here is another example, but this is an example where the functional does not have the property given in the conclusion of proposition 2. Let's just show you this property, this important property, that f of phi turns to infinity when the norm turns to infinity. So let's give you a really simple example where this happens. For example, for the function f2 of x equal to the exponential function of minus x squared, this function, the graph of this function is illustrated here. And we see that this function does not have the property that when x approaches infinity in absolute value, that this function will approach infinity. As a matter of fact, it turns to 0, so it does not go to infinity. However, the function is continuous. So this function had the property that f1 of x goes to infinity when the absolute value of x goes to infinity, but did not have the property of being continuous. This is the opposite here. The function has continuity but has not this property. So these two examples shows that both of these properties should be satisfied, or the function should have both this property in order to ensure that we have a minimum point.